Keeping with the theme of MoQ here, we're going to talk a little bit today about leveraging our structured concurrency framework to actually implement a player that supports MoQT. So this was, I'm from Bitmoving, by the way. My name is Matthew, and I'm a solutions architect, so this was actually done by our engineering team. Most of them were not able to travel here, so I'm doing this kind of on behalf of them. So bear with me on that. Let me go forward here. So obviously, there's quite a few different, drafts or specs involved in MoQ. What we're really kind of interested in, or the components that we're interested in today, are MoQT, so the MoQ transport, as well as the streaming format, whether it's a low overhead container or the CMAF compatible version of that. So MoQT is really defining the protocol of how we're receiving the data. And that kind of consists of these three main components, which you can see up here. Obviously, there's a publisher who's actually pushing the content to a relay. That relay is then responsible for distributing the content. And of course, then you have the consumer, who can subscribe to one or more of the tracks that is coming from the publisher. This data also needs to be kind of organized in a specific way. So the publisher can publish one to many namespaces. And within each of those namespaces, you can publish various tracks. So these are going to be obviously media tracks. And within each of those tracks, you have one-to-many groups. And those groups, depending on how many groups you have, kind of just depends on the format of the data that's being transmitted. And so then finally, within each of those groups, you have a set of objects. So the transport part here is kind of defining how, and the MoQ streaming format and CMAF version are really kind of talking about what and the format of that data. So as you can kind of see here, we have a set of tracks. The first and most important track that we need to look at from a player standpoint is called a catalog track, and it's really just kind of describing what the other tracks available are. So those are going to be media tracks, audio tracks, video tracks, could be other types of media tracks as well. And then from those tracks, we have our groups, right? And in the context of video, the groups that are being sent as part of MSF are the actual group of objects, right? And then the objects within that group are the individual frames from that. Sorry, here. So as we tried to look at building a player to support this, the first thing that we needed to do was have kind of a test harness, right? So what we knew we wanted to do right out of the gate was to be able to support track switching. So basically being able to have multiple quality renditions that we can switch between. So what we use as a test harness is we use basically OBS to kind of be our contribution source, which was pushing RTMP to a RTMP server, which is finally then fed into FFmpeg. And that FFmpeg is obviously doing the actual ABR renditions that are available. So I think we did basically 2 HD renditions and 3 standard definition tracks within there, as well as obviously an audio track. And then FFmpeg is then pushing that using the MoQRS library to a relay. So we went with a public relay hosted by Cloudflare for obviously ease of testing here. Also to note, with the packaging, we use CMAF packaging, and we were doing 30 frames per second content with a GOP size for every 15 frames. That way, kind of a nice trade-off for GOP size for latency and everything. Most of what we're focusing on is the CMAF version of the MoQ streaming format, but I will mention some stuff for some future work that we're doing with the low overhead container for that. All right, so why did we want to do this with our, with our new player WebEx that is built on a structured concurrency framework? So we decided to implement this because our new structured concurrency framework allows us to, together with the state-driven architecture, allows us to actually implement some of these use cases quite quickly and easily. This player is also kind of a plug-in first approach, so all of the MoQ support that we built in was actually done through plugins. So we didn't actually have to get like under the hood and change any of the source code from our existing player that supports standard HLS and Dash streaming. This structured concurrency framework also allows us to run all of the code that's associated with parsing and dealing with these tracks as tasks, and those tasks can be subscribe to a specific state of the track. So if we want to activate a new track, we can automatically execute a series of tasks or code that has reference to the state of that track. So if we want to unsubscribe from that one and subscribe to a new track, we can do that easily, and all of the code behind that is either automatically executed or automatically cleaned up, depending on which track we're unsubscribing from or subscribing to. So for our player, we decided to implement this based on version 7 of the MoQ draft. That's using CMAF packaging. And for the actual transport handling within the player, we decided to use a pretty lightweight library called MoQ Lite, which doesn't really implement the entire MoQ spec, but it at least has kind of the core components that we need. That's kind of called MoQ Lite. So the actual handling of these MoQ tracks looks like this. The first thing we do, obviously, is we want to parse that catalog track. That tells us what all the other tracks are available. We take each of those available tracks and we represent that as their own state object. That means that we can set up listeners for those states. Like I was mentioning earlier, we can set up a listener for the specific state and handle automatically any of those changes within the state of that catalog track. The states that we kind of set up for this are basically an active state, so basically saying this is the track that we want to subscribe to, inactive, and then there's also a third state, we call it suspended, and then we'll talk a little bit more about that here in a minute. So as you can see here in the graphic, there is basically 3 video tracks being shown, and only one of those is active, and the other ones are inactive. So let's say we are playing back a 720p track rendition, and we want to switch to, say, a 1080p track rendition. All the cleanup from the track set, the 720 being inactive, is handled automatically, and any tasks that need to run as part of processing the new track are handled automatically. One second here. All right, for each track that's set to active, we're going to basically, the way we're going to process that is through a series of tasks. Or there's going to be a root task that gets spawned for whenever a new track becomes active, and then there's subtasks that are tied to the state of that root task. So those subtasks are going to go kind of in order of consuming all of the groups from a specific track. So first we're going to have a consumer task that handles consuming those groups. And then from each of those groups, we'll have a new task that's going to handle consuming all of the objects or the frames from that. We call that a frame consumer task. So considering that we're dealing with the CMAF packaging format here, the content of those actual objects are CMAF fragments. So first we have to demux those, right? So we have a demuxing task that's using MP4 box to actually extract the encoded frames from those fragments. Once we have the encoded frames, the next thing we have to do is decode them, right? So we're using the web codecs API to basically there's a video decoder and an audio decoder APIs within that are available, and we're using those to handle the actual decoding of those frames. Finally, we end up with a set of decoded audio and video frames, and we need to be able to store those into some sort of buffer, right? So we've created a frame buffer. We have an audio frame buffer as well as a video frame buffer, respectively. And we're going to fill that buffer with all the frames from that last processing task. This also ensures that any of the consumed frames that we have are cleaned up properly, so that any of the resources that were being held up in consuming those are freed after they've been used. So since we're using the web codecs API here, and we're handling all this kind of processing asynchronously, right? So these audio buffers as well as the video buffers, these are being filled independently. So before we can try to render any of the audio or the video, we actually need to synchronize those tracks. In order to do that, we came up with a timing source that will handle essentially cataloging a offset of the presentation time from the fragments versus a wall clock time in the timing source. So this timing source can kind of operate in 2 different modes. The most common one would be as long as you have audio, we're going to use the current time from the audio context API to use that to set our internal clock. So now we can have an internal clock, and we have the presentation timestamps from the frames, and we're going to map those as offsets. If there is no audio track for whatever reason, we can just use the DOM high-res timestamp for just the video internal clock. But either which way, basically what happens is whenever the first frames come in, we're going to use the PTS time from those and map that against our internal clock from the timing source. So now we always have a way to understand what the timing offset is between those PTS stamps. And that allows us to synchronize video with the audio. All right. So now that we have the synchronization between audio and video, and we can track the timestamps, we can actually look at how we render those. So conceptually, the rendering task is essentially a kind of an infinite loop that's always awaiting the next frame for a given time to become available. And so the timing source is obviously helping feed into that processing loop, so that as the frame becomes available, it can get scheduled for rendering. The rendering itself varies quite a bit, obviously, between audio and video. So for video, it's kind of simple. We're basically just going to take the frame and render it onto a 2D drawing context. But the audio is a little bit more complicated. You don't just directly render audio. You actually have to schedule it for a specific playback position. So the audio rendering task is taking the next frame from the frame buffer, and it's calculating the start time of that frame based off of a reference frame in the audio context. So then it can be scheduled for playback at exactly that position. One little caveat with that is that if you need to do something like pause the video, right, because you are scheduling audio for a playback position, that has to be kind of manually cleaned up. So like if you need to pause it, you have to manually clean that up so that it doesn't continue to play. So just kind of talking about some of the use cases that we aimed for on here. So obviously this was a use case for live low latency streaming. We have not yet kind of tackled the on-demand or VOD or DVR piece of this. That's kind of coming up next. But what we did want to be able to come out right out of the gate with is audio quality switching and as well as background playback. So whenever we need to switch qualities, that's very easy to do with our structured concurrency framework. You can basically just subscribe to the new track, and all the subtasks that are associated with that will automatically start and stop from anything that's unsubscribed. We also can use like the page visibility API, so that if you're watching a stream and you go to another page, we can actually suspend we can put the state into a suspended state for just the video track, but allow the audio to continue to play back. So the video track can be suspended, audio is still playing, and you can get that backgrounded kind of audio experience. The other thing we wanted to try to do, since we were working with CMAF here, was see if we could introduce backwards compatibility to the MSE. The reason for that is obviously the MSE already is like a very optimized for video playback, and it comes with like the timing source that for working with the web codecs API, we had to build the timing source ourselves. But MSE has all that. It also has the ability to work with the EME to handle any kind of DRM encryption. So the encrypted media extension we can use along with the MSE for that type of, as long as we're using, of course, the CMAF packaging here, we can utilize that. So we did test that out. It actually worked really well. The one kind of caveat we found was that we had to basically append entire GOPs to the MSE in order to get playback to work. So when we were working with the web codecs API, we could handle that on a per frame basis. But with the MSE, we did find that we had to append entire GOPs. So obviously, depending on the size of the GOPs that you would be using in a real-world situation, it can add a little bit of latency there to have to append it in a full operation, entire GOP. Looking at kind of the experimental results that we had, we were able to achieve a latency out from the output of the encoder to the frame buffer of less than a second, so about like 800 milliseconds. We did end up, having a little bit of a frame buffer where we kind of played around with some different values and came up with a pretty good compromise of just only 300 milliseconds worth of buffer time. And so that put us at a total latency from the output of the encoder to the playback of around just over a second. So that, that gave us like kind of a pretty similar latency aspect as what you would get from like WebRTC, even better than what you would get from, you know, low latency, you know, specs like for HLS and Dash. So in conclusion, this is how we essentially were able to use our structured concurrency framework and our state-driven framework to build out support for MoQ, as well as not having to touch the underlying core player that was, you know, previously built for HLS and Dash, and we can also use both web codecs and the MSC for playback with pretty aggressive latency targets. Some of the things that we're looking to kind of continue with are obviously we want to also introduce the support for not just CMAF, but the low overhead containers, so just the you know, MoQ streaming format, because the low overhead container has some pretty good advantages when working with the web codecs API. It's you know, it doesn't need to be you know, you don't have to use something like MP4 box like we did to demux that or anything. What the low overhead container offers is basically just the raw frame plus some timing information and then a header, so that works very kind of naturally with the web codecs API. We also want to do some optimizations around you know, track switching and figuring out how we want to handle ABR. I think we saw in the last talk, you know, there's a lot of different ways people are looking at ABR. Some of it is kind of inherent to the network. There's also some other ideas out there. So as those kind of ideas, some of those maybe get standardized or become popular, we also want to look at sort of how we can handle ABR within this situation. We also want to update to newer versions of the draft. So I mentioned earlier we were on version 07 of the draft. That's also what I think the relay was being based off of as well from Cloudflare. So it kind of made sense, but of course we want to keep up with newer versions of that draft. All right. Well, that was the end. All right, thank you, everybody.
Okay, thanks, Matt. One question, if one. No, next. Okay.
No question.
Any question? Oh.
What were the sort of segment lengths essentially like in the CMAF?
0.5 seconds. So basically identical to our GOP length, which was 15 frames for 30 FPS content.
So did you? So when you said you sort of, did you actually implement it using MSC as well as web codecs? And
We've
you just
got,
said,
yes,
yeah.
We've got a working web codec implementation. There's, I think, a demo for that. I'm not sure if it's public. We tested with the MSC implementation. We've got a demo for that as well, but that's not as fleshed out as the web codec implementation. Basically, what we wanted to do is we wanted to validate that it does work with the MSC. This was our main goal, and this is what we did.
Because you get around all the sync problems there as well, because MSC just handles that, yeah.
Yes, like synchronization, you don't have to worry about any of that. The MSC can stall. Like if you're using web codecs for rendering, of course you have to stall manually. There's like no built-in stalling mechanism and stuff like that, yes.
Right, but you said you found that you had to load an entire GOP. I mean, that's
Yes.
not, I mean, I'm not, is that just on that platform you were testing, or because
We were testing in Chrome on macOS. Like our assumption was, we configured FFmpeg to not use B frames, so it should only have been I frames followed by P frames, which should have been perfectly decodable. Like every time you append one of the frames, they should have been decodable given the iframe was appended. But that didn't work. If we did that, the iframe was rendered on the video, the P frames were not. There could be additional factors that like play into that, like with our setup. But like this is definitely what we saw with our experiment setup.
Unless it was a timing thing, sort of the duration or something, because I mean, in say for Dash.js, for example, it dumps in the chunks, and the chunks aren't necessarily full GOPs, and they does start playing before.
I mean, the way we got it working is by just concatenating all of the individual CMF chunks that we got. Like we didn't modify them, we just concatenated them and then appended them, and then it worked. It's appending them individually didn't, but concatenating them and appending them that did work in the end.
Okay, thanks. You said it's open source, or?
No, it's not open source.
Okay,
I mean,
fair enough.
I mean, we can make parts of the implementation open source. We haven't yet.
Thanks.
Okay, due to time constraints, so no more questions. Next presentation.